Welcome students to the computer science class. In this tutorial, we will discuss the exercises on the chapter number system. After we have done with the chapter, it's time to discuss the exercises. Now you see I have made a Word file solving the exercises for you, and I will briefly describe and explain each answer that has been written in this document. So let's begin. The first one, tick the correct answers. Computers recognize only two discrete states, yes and no. The options are yes and no, right and wrong, on and off. The answer will be on and off. So there are two discrete states, on, power is on, and the power is off. So the computers can recognize only two states, on and off. Next one, the on and off states are represented by 0 and 1, 0 and 1 1, 0 0 and 2. The right option is, you all know, it's 0 and 1. The on and off states are represented by 0 and 1. Next, the digit 0 represents the electronic state on, off, none. The digit 0 represents the electronic state off. The group of 8 bits forms a megabyte, byte, gigabyte. Group of 8 bits is a byte. You all know a group of 8 bits is a byte. So a group of 8 bit forms a byte. The collection of bits on a 4-bit boundary is bit byte nibble. Answer is nibble. The smallest unit of data is byte, beat, nibble. It will be bit. The smallest unit of data is bit. That is a 0 or a 1. That is the smallest bit of data that a computer can understand. It is a bit. The base 10 number system is binary, hexadecimal, decimal. The base 10 number system is decimal. Binary is a base 2 number system. Hexadecimal is a base 16 number system. And decimal is a base 10 number system. Why? Because in decimal we use 10 digits. There are 10 different digits or symbols used in decimal number system. That is from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So 0 to 9 there are 10 different digits that are used in decimal number system. So the base of the number system is 10. The number system used internally by all modern computers. The number system used internally by all modern computers are, what is the number system? The options are hexadecimal, binary and octal. The correct answer is binary. So the number system that is used internally by all modern computers is the binary number system. The digits used in octal number system, how many digits? There are 8 digits, 0 to 7. So the digits used in octal number system are 0 to 7. So number 3 is the correct answer. Write true and false for the following statements. The decimal number system has just two unique digits, 0 and 1. It is false. Why? Because decimal number system has 10 unique digits from 0 to 9. Right? So what is the correct statement? The correct statement is the decimal number system has 10 unique digits, 0 to 9. B. The smallest unit of data is a bit. It is true. The smallest unit of data is a bit, that is either a 0 or a 1, that a computer can understand. A byte is used to represent a single character in the computer. It is also true. To represent a single character, we need at least one byte to represent a character. So each of the characters on the keyboard, you can see, are represented in the memory with a 1 byte of memory, that is 8 bits is equal to 1 byte. 8 bits are required to represent a character. A group of 8 bits is called a kilobyte. A group of 8 bits is called a byte. It is not a kilobyte. A group of 8 bits is called a byte, only byte. It's not kilobyte. So it is false. Next, a nibble is a collection of 5 bits. It's a collection of 4 bits. So it is false. Next, fill in the blanks. Dash number system can be represented by few symbols called digits. It is the positional number system. Positional number system can be represented by few symbols called digits. Right? It is only in the positional number system that we find the digits or symbols. But what about non-positional number system? Any digits or any kind of symbols, anything can be used to represent the values. So the additive approach is used in a non-positional number system. So there is no specific set of symbols or digits used in case of non-positional number system. The early men used the non-positional number system where they used only the pebbles and sticks to count the numbers, to count the value of the representation made by sticks and pebbles. But in case of positional number system, we have few symbols, fixed set of symbols dependent on the base of the number system. Like in decimal number system, we have 10 symbols. Next, The decimal number system has dash as its base. It has 10 as its base. As there are 10 symbols, the base of the decimal number system is 10. The dash number system represents numeric values using two symbols, that is 0 and 1. The binary number system represents the numeric values using the symbols 0 and 1. Next, the dash number system is base 8 number system. The octal number system is base 8 number system. There are how many symbols in octal number system? There are 8 symbols or 8 digits, 0 to 7. So octal number system, the base is 8. In number system, hexadecimal is the number system with a base 16. So hexadecimal is the number system with a base 16. There are 16 digits in hexadecimal number system, 0 to 9, A to F. 0 to 9 there are 10 digits, and 10 to F there are 6 letters. So these are also symbols. 10 is written as A, 11 is written as B, 12 is C, 13 is D, 14 is E, and 15 is F. So like this, there are 16 different symbols in hexadecimal number system. Next one, answer the following questions. Explain the binary system. Explain the binary number system. So you have to write about binary number system here in a precise way. You have to, while writing the answer, you have to give a short definition, and then you have to write about its base and how to represent numbers using the digits of the binary numbers, that is 0 and 1. So let's see. Explain. You have to explain. So first give a definition. A binary is a base 2 number system, and it uses the symbol 0 and 1. Each position in a binary number has a place value associated with it. The place values moving from right to left are successive powers of 2. To give emphasis on this, the place values moving from right to left. So you will move from right to left. Okay? Right to left means if this is the binary number, you have to count from here. This is 0, this is 1, 2, 3, like this. Okay? So from right to left, you have to count. Are successive powers of 2. That is, the power is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, like this, and so on. However big the representation is, you have to go on counting, like from 2 to the power 0, this one is 2 to the power 0, right? The next one is 2 to the power 1. Next there is a 0, it is 2 to the power 2. So 2 to the power 2, there is a 0. Next, there is a 1, 2 to the power 3. This one is at the place value 2 to the power 3. Right? So in this way, it is counted 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on. And what are the values? 2 to the power 0 is 1. Anything to the power 0 is 1. Right? So 2 to the power 2 is also 1. Next is 2 to the power 2. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16. So the values are written respectively. You see 2 to the power 0, the value is this one. Right? 2 to the power 1, the value is this one. 2 to the power 2, the value is 4. 2 into 2, it is 4. 2 to the power 3, 2 into 2 into 2, it is 8. Right? 2 to the power 4, it is 4. Multiply 2 4 times. 2 into 2 into 2 into 2, get 16. Right? So when you multiply 2 4 times, you get 16. So we construct binary number by placing ones in the positions where the corresponding values add up to the quantity we want to represent, and by placing zeros in other positions. Very important. So that is a complete explanation of the formation of binary numbers. How we construct binary numbers? We construct binary numbers by placing ones in the positions where the corresponding values add up to the quantity we want to represent, and by placing zeros in other positions. So wherever we place a 0, it will not give us any value, it will be a 0. So when we want to represent the number 11, we have to place a 1. You have to start placing a 1 from the highest place. For example, you have to represent 11 with 4 bits. There are 4 bits, you can see 1, 1. Here, start counting from here. 1, 2, 3, 4. So there are 4 bits. 4 bits in this number, and you have to represent with 4 bits the number 11. Right? So how to represent? You have to have 8 here. This is 2 to the power 3. What is this position? If you count, this is 0, 1, 2, 3. So maximum you will have 2 to the power 3. So place a 1 in the position 2 to the power 3. So you get 8. Now if you place another 1 in 2 to the power 2's place, then what will be the value of 2 to the power 2? It is 4. So if you add up 8 and 4, you will get what? You will get 12. So it is more than the number you want to get. You want to get 11. So you will not place a 1 in 2 to the power 2's place. Right? So you will place a 0 at that position. So our 0 is placed. Next, this is 2 to the power 1's place. This is 2 to the power 1's means the value is 2. So add 8 plus 2, you are getting 10. Okay, so place 1 into 2 to the power 1's place. Now the value is 10. In 2 to the power 0's place, what is 2 to the power 0? It is 1. So you need what? You need only 1. So you place another 1 to get 11. So in this way you can create a binary number. So we construct a binary number by placing ones in the position where the corresponding values add up to the quantity we want to represent, and by placing zeros in other positions. So we placed a 0 in the position of 2 to the power 2, as we don't require a 4 in our representation after we have got 8. So it will give us a more value that we want. So we'll give a 0 in that place and we will give 1 in the places we want to get a respective representation, respective value for the number, right? So let's read the explanation of binary number system once again. The binary is the best two number system and uses the symbol 0 and 1. Each position in binary number has a place value associated with it. So you have seen each position is having a place value. The place values moving from right to left are successive powers of 2. You have seen how they are successive powers of 2 and how you add up the powers of 2 to get the value of the representation in a binary number. Next, we construct a binary number by placing ones in the positions where the corresponding values add up to the quantity we want to represent and placing zeros in other positions. The example is this number. So use this as example, or you can use any other binary number as example and explain it like this. Right. Now someone's question may be, do we need to use this calculation? Now as they have asked you to explain, that's why I have made this example. But if you don't want to give only write this number as the example, then it is fine. If it is difficult for you, I think it should not be difficult, as you have understood the conversion, how you are getting 11 from this number. Still, if you feel, you can write only up to this. The example is this, and right, it has ones in the positions for the values 1, 2 and 8. You can see in the positions 1, 2 and 8, that is 2 to the power 0, 2 to the power 1 and 2 to the power 3. So it is having ones in the positions 1, 2 and 8 and has a 0 at the place value 2. So the number is 8 plus 2 plus 1 is equal to 11. So that's it. Up to this you can write, or you can write the complete one. Okay. And you can also make your own answers. That is more advised and that is more appreciable. Yes. The next one. Differentiate between decimal system and a binary system. So you have to write the points of differences between a decimal system and a binary system. The base 10 number system and the base 2 number system. So that is one point of difference. It is a base 10 number system, decimal system, and binary system. Under binary system you write it's a base 2 number system. Under decimal number system you can write 10 digits from 0 to 9 are used to represent the numbers in decimal. In binary number system, only 2 digits are used to represent the numbers in binary, that is 0 to 1. In decimal number system, the place values moving from right to left are successive powers of 10, right? as you get ones, tens, hundred, thousands. They are successive powers of 10. Ones means 10 to the power 0. Tens means 10 to the power 1. 100 means 10 to the power 2. 1000 10 to the power 3. 10,000 10 to the power 4. So like that you go on moving from left to right. They are successive powers of 10 in case of decimal number system. The place values in a binary number system moving from right to left are successive powers of 2. That is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4 and so on. That is 2 to the power 0 is 1, next is 2, next is 4, next is 8, 16, like 32, 64, 128. In this way you move on from the place values one after the other successively. Okay, so write the 3 points of differences. Next, define the following terms. What do you mean by a bit? A byte and a nibble. So these are very simple definitions. A bit refers to a binary digit in binary number system. It is the smallest unit of data that a computer can represent. So it is the smallest unit of data a computer can. Bit is a binary digit, 0 or a 1. Byte, when 8 bits are grouped together, it is zeros and ones, 8 bits like 8 zeros or 8 ones or a combination of them are grouped together as a unit, they form a byte. When 8 bits are grouped together as a unit, they form a byte. It provides different combinations of zeros and ones to represent 256 individual characters. Why 256? Because there are 2 bits, 0 and 1, and if you make a pattern which is 8 bits long, then you can make how many combinations? You can make 2 to the power 8 combinations, and 2 to the power 8 is equal to 256, right? So this is just a note. I will write it over here. How I get 256? It is 2 to the power 8, right? It's a note. You don't have to write it in your definition of a byte, but it is for your understanding, just a note, right? Don't write it in your answers. Next is nibble. Half a byte is called a nibble. A nibble is a collection of bits on a 4-bit byte. So half a byte is 8 bits long. A nibble is half of it. That is 4 bits long. So half a byte is called a nibble. Next, name 2 categories in which number system is divided. The 2 categories in which number system is divided: non-positional number system and the positional number system. Non-positional number system used by the early men. They used an additive approach to count the numbers, and the positional number system is used by us. Examples are the decimal number system, the binary number system, the hexadecimal number system, the octal number system. All are positional number systems, right? So the 2 categories of number systems are non-positional number system and positional number system. Next, name different number systems used in positional number system. Yes. Different number systems that are used in positional number systems are binary number system, that is a base 2 number system, octal number system, base 8, that is 8 digits are used, 0 to 7, decimal number system, base 10, 0 to 9, there are 10 digits, hexadecimal number system, there are 16 different digits or symbols used in this number system. It's better to say symbols than digits because all are not digits, but there are also letters used in a hexadecimal number system. As you know, 0 to 9 are the numerals that are used, and A to F are the letters that are used. Capital A to capital A to represent A to 15. A is written as capital A, B is 11, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So from 0 to F there are 16 different digits or symbols. Next, what is the base of decimal number system? Deci means 10. Base of decimal number system is 10. What is the base of octal number system? It is 8. 0 to 7. There are 7 digits. There are 0 to 7. There are 8 digits, right? Used in octal number system. 0, 1, 2, 3, 4, 5, 6, and 7. So there are 8 digits. Base is 8. Next, differentiate between positional and non-positional number system. In a positional number system, there are a few symbols called digits. In non-positional number system, we use symbols such as 1 stick for 1, 2 stick for 2, 3 sticks for 3, and so on. So each of the sticks has got the same value in the number irrespective of their position. So there is no other value for different sticks. All represent the value of. So an additive approach is used to count the value in non-positional number system. The number of symbols used depend on the base of the number system. For example, in binary only 2 digits are used. In octal 8 digits are used. So in binary the base is 2 and in octal the base is 8. So it is in positional number system. Both are positional number system. In non-positional number system, only one symbol is used for counting the value in an additive approach. So either it is a pebble or it is a stick. If you are using a pebble or you want to represent 50 by pebbles, you accumulate 50 pebbles and count 50 so that the representation is 50. So only one symbol is used and the approach is additive. So each of the representation or each of the symbol is having a value 1. Next, in positional number system, the digits represent different values depending on the position they occupy in a number. Right? The digits represent different values. Like if 2 is in 1's place, it is only a 2. If it is in 2's place, it is 20. it is in tens place it is 20, if it is hundreds place it is 200. So like that, it is the value depending on the position they occupy in a non-positional number system. Each symbol represents the same value regardless of its position in a number. Right? Each symbol represents the same value, that is 1. Or if it is some other value, it is the same for all the positions. So based on the positions, the values will not be different, like in positional number system. Okay? Next. Next one. Convert the following: decimal to binary. Right? You have to convert a decimal number to a binary number. So you have already known how to convert a decimal number to a binary number. See, the numbers are given: 345, 113, 145. 145. So how to convert 345? How to convert 345 in decimal to binary? 345 is in decimal. You want to convert it to a binary number system. What is the base of binary? It is 2. So we will divide 345 by 2. So go on dividing till you get a 0 and collect all the remainders on the right hand side. So when you divide it by 2, you will get 172. The remainder is 1. Again you divide it by 2. The remainder, you will get quotient 86. Remainder as 0. Again you divide it by 2. Right? In this way? Right. So you will divide again. You will get 21 as quotient and 1 will be remainder. 21 to the 40. Again divide, you will get 10 as quotient, 1 as remainder. Again 5 as quotient, 0 as remainder. Divide again, you will get 2 quotient, 1 remainder. Again divide, you will get 1 quotient and 0 remainder. So you will divide again, so cannot, you will get 0 and you will take this 1 here. You cannot divide 1 by 2. So you just take this 1 to the remainder, right? So you have taken this 1 over here. Now what you have to do, you have to write these remainders in the reverse order. That is in the order, just reverse in the way you have got. Not in the way you have got, in the reverse order of the way you have got. So you have got this one first, then you have got this. So you will not write in this way. You will write 1 0 1 0 1 1 0 0 1. See, 1 0 1 0 1 1 0 0 1. So it is written in this direction. In the reverse way order, how you have got the remainders. Okay. So similarly, you have to do it for 113. You have to divide 113. You can see it is divided in the same way, and you have to collect the remainders, and then you have to write the remainders in the reverse. Okay. Next, you can cross check. After you have obtained the representation, you can cross check whether this representation you have got. I will not do this cross check for this number 345. I'll do it for 130. See, I will cross check. To cross check, I have to write the position values. I have to calculate the position values where there is a 1. See, where there is a 1, 2 to the power 0, this is 1, 2, 3, 4. 2 to the power 4, 2 to the power 5, 2 to the power 6. So, let's write 1, 1, 1, 0. Now let it position it here, right? We are doing this one, we are doing this, we are checking this representation. So we are checking that whether we can get 113 from this one or not. So 1110, then 001, right? So where are the ones? Ones are in the places 2 to the power 0. We will start from writing 2 to the power 6, right? You can see I have written it over here. 2 to the power 6 into 1. So don't write into like this, you have to do it mathematically, right? Into 1 plus 2 to the power 5 into 1, right? Then plus 2 to the power 4 into 1 plus, there are zeros. For 2 to the power 3 there is a 0, plus for 2 to the power 2 there is again 0, for 2 to the power 1 again you have a 0. Next, in 2 to the power 0 you have 1. 2 to the power 0 means 1. So like this. Next, you have to find what is 2 to the power 6. 2 to the power 5 means 32. 2 to the power 6 means 64, right? 2 to the power 6, 64. Plus 2 to the power 5 is 32. Plus 2 to the power 4 is 16. Plus 0 plus 0 plus 0. There will be 3 zeros plus 1. Right. Next, add up 16 plus 32 plus 64. It is 113. Isn't it? Right? So you have got 113 back from the representation you have calculated. The binary number you have calculated, you have got back the decimal number from that binary number. So your calculation is okay. So in this way you can cross check. Next is binary to decimal. Okay, we have to convert a binary number to decimal number. That's what we have done while rechecking. We have done that only. That is binary to decimal conversion. What is rechecking? Rechecking means doing that. So we will do that for the numbers given in the exercise. For 111, see, we have ones in the places for 2 to the power 0, 2 to the power 1 and 2 to the power 2. So 4 to the power 2 is 4, to the power 1 is 2 and to the power 0 is 1. It is 7. 7 in decimal. So don't forget to write the base in the suffix, right? This is not 112. This is 111 because the base is 2. Notice the base. If it is in 10, if the base is 10, then you could have called this 110 or 111. But you cannot call it as 111 because this is not an 100. This is a far lesser number than 100. This is only to the place value, the positional value of this one is not 100. It is 2 to the power 2. That is only 4. Right? But if it is 10 base, then it is 100. So that is the difference, right? In the different number systems, from difference in binary and decimal. Next, you convert this number 1101. We have ones in the places 2 to the power 3, 2 to the power 2 and 2 to the power 0. And there is a 0 in 2 to the power 1's place. So we will get a 0. So for 2 to the power 3, 2 to the power 2 and 2 to the power 0, we will write 8 plus 4 plus 1 equal to, we got 13 in decimal. So again I am telling, don't forget to write the base. So in this way you will also do for 1000. That is the representation having 1 only in 2 to the power 3's place. That is, it is equal to 8. All other are 0. You contribute to 0 to the sum. It is 8 in decimal. Next, you do the decimal to octal conversion, right? Let's convert decimal to octal. Number C, right? What do you have? 45, 70, 220. See, I am telling it is 45, 70, 220. Why I can tell this? Because they are in decimal. See, it is written decimal to octal. So the numbers are given in decimal. You are to convert the decimal number to octal numbers. Okay? So like we call in our day-to-day life the numbers, we refer to the numbers, we can 45. So 45 into octal, how you can convert? You have done for our binary, you have divided the decimal by the base of the binary number system. Similarly, here you will divide the decimal number with the base of the octal number system. Right? What is the base of octal number system? It's 8. So divide 8. Divide 45 by 8. You will get 5 as quotient and 5 as remainder. Again, you cannot divide. So bring this 5 in the remainder and write the remainder in the reverse order you have got. So it is 5, 5 in octal. See, I am not telling 55, I am telling 5, 5. Tell 5, 5. Right? So 5, 5 in octal. The base is 8. 45 in decimal is 55 in octal. Next you again see over here 70 in decimal. Divide 70 by 8. We will get 8 as quotient and 6 as remainder. Right? Again you divide that 8. You will get 1 and remainder 0. So bring this 1 to the remainder and write the remainder in the reverse order. 1, 0, 6. So this is the number in octal, equivalent octal to 70. So 70 in decimal is 106 in octal, right? Okay, okay. So you can divide by 8 to convert a decimal into a octal number, right? And you can similarly cross check. The cross checking can be done. So I have written here, you can see, do number 3 on your own. You will do number 3 on your own. That is, you will divide 220 by 8 and do it. See, 106. I have found out that 106 is the equivalent octal number. 106 is the equivalent octal number, equivalent to 70 in decimal. So have I done it correctly? I will see. I have to cross check. 106. So what are the positional values? 6 is 8 to the power 0. 0 is 8 to the power 1. 1 is 8 to the power 2. So 8 to the power 2. 8 to the power 2 plus 8 to the power 2, you have to do 8 to the power 2 into 1, right? Next, 0 plus 6 into 8 to the power 0. Anything to the power 0 is 1. Right. So that is what we get. So 8 to the power 2, it is 64 plus 48. Right. 64 plus 48. It is, see, 8 to the power 0 means what? 8 to the power 0 means 1. Anything to the power 0 is what? It is 1. So 6 into 8 to the power 0. 8 to the power 0 is 1. So 6 into 1 is 6. Right? So you have got 6 from this and you have got 64. 8 8 is 64 into 1. 64 from this. So the value is 64 plus 6 is equal to 7. So 70 you have got. 70 is in decimal. So like that you can cross check, okay, and do the third one on your own. And the last one, you see, decimal to hexadecimal conversion. So you have to convert a decimal to hexadecimal. And this is also done in a similar way. You have done the decimal conversion, decimal to binary. You have done decimal to octal. Now we will do decimal to hexadecimal. So what you have to do? You have to divide the decimal number with the base of the hexadecimal number. That is 16. Like you remember while you done decimal to binary, you divided the decimal with the base of the binary. That is, you have divided that by 2. Now you will divide it by 16. So divide 22 by 16, you will get 1 as quotient and 6 as remainder. So carry this 1 over here on the remainder side and write it in the reverse order. What is the hexadecimal equivalent? It is 1 6. So 2 in decimal is equal to 1 6 in hexadecimal, right? Again, you do it 330. 330 in decimal, you want to convert it to hexadecimal. So divide it by 16. 16 to the 320. So 16 20 is a 320. You get 10 as remainder. Again divide 16. Divide 20 by 16. You will get 1 as remainder. 1 as quotient, and we will get 4 as remainder. So carry this 1 in the remainder side. You will get 1410. So 1 4 are the individual remainders. See. And 10 is an individual remainder. So how is 10 written in hexadecimal? It is written as A. So it will be 14A. You will not write 10, you will write A. 14A. That is in hexadecimal. Similarly, you also do it for 840. Okay. You will also do it for 840. Here you will get 3 will be coming in the remainder side. You will get 3 4 8, right? So that is what it is written. So in this way you do the conversions, and if you come across any doubt, if you have any doubt, comment it. I will make another video on it to clear your doubts. Okay, all the best. Do the conversions, solve the exercises. Thank you all.